Okay, part 2 on roots and radicals is properties. So in the book, they'll give you something like radical A over radical B is equal to radical A over B. Which means if you have a radical in the numerator and a radical in the denominator, and they have the same index, in this case they're both square roots, you could write it as a single radical over the entire fraction. And inversely, we could do the opposite, right? We could say if I have a fraction, whatever, a over b, I could break that up as square root of a over the square root of b. So some examples of this, if I had the square root of 1 over 25, or the fifth root of 1 over 32, let's see, or if I had the square root of 75 over the square root of 3. If I had, we already did one of those, but I don't know, square root of 4/9, maybe the cube root of 16 over the cube root of 2. So here's 5 examples we could look at and apply these properties. So in this first example, radical 1 over 25, we could break up as the square root of 1 over the square root of 25. The square root of 1 is 1, and the square root of 25 is 5. Similarly, in this problem, we could take the fifth root of 1 over the fifth root of 32, and the fifth root of 1 is 1, and the fifth root of 32, 2 times 2 times 2 times 2 is 32, so that would be 1/2. So the fifth root of 1/32 is equal to 1/2. In this case, we have radical 75 over radical 3. The square root of 75 over the square root of 3. And there is no square root of 75, so this problem could be done another way. It could be done by simplifying the top and looking for common factors. But the easiest way would be to write this as a single fraction. Maybe I should do it down here. If I write it as a single fraction, 75 over 3, well, 75 divided by 3 is 25, and the square root of 25 is 5. Right? So it'd be easier to write that. So there's no one right way to do it. This is just a simpler way, and if you're able to see it, that's great. And if you're not, we could have done this by breaking up 75, right? Simplifying this fraction as rad 25, rad 3, and canceling out. We would have come up with the same answer. Here I have the square root of 4 over the square root of 9. And I know the square root of 4 is 2, and the square root of 9 is 3. So in this case, we have 2/3. And in this example, we have a cube root and a cube root. I could write this as a single cube root of 16 over 2, which is the cube root of 8, and the cube root of 8, 2 times 2 times 2 is 8. Cube root of 8 is 2. Also note, with multiplication, which we kind of did when we were simplifying radicals, we know that if I have two radicals with the same index, I could multiply them. This is square root AB. So the square root of A times the square root of B is the same thing as the square root of A times B. So that's something that we kind of went over when we were simplifying radicals. Let's do some examples, some more examples. Here's some more examples you could try. Maybe right now you want to pause this video and try these 4 examples and then restart it, and I'll go over how to do them right now. So in this first example, it's the square root of 1 over 49, which is equivalent to the square root of 1 over the square root of 49, which would be 1/7. Our second example says the square root of 121 over 9. So I could break this one up as the square root of 121 over the square root of 9. The square root of 121 is 11, and the square root of 9 is 3. So I get 11/3. In this example, it's the square root of 72x to the third over the square root of 8x. Well, the easiest way to do this would be to write the whole thing under 1 radical as a fraction, because I know 8 goes into 72 9 times, right? So I could simplify this. It would be the square root of 9. And here, my properties of exponents, when I have x to the third over x to the first, I keep the base, I subtract my exponents, so I'm going to have x to the second. So in this case, I have a perfect square, square root of 9, and x squared is a perfect square. So square root of 9x squared, 3x. Similarly, with the next one, we have 2 radicals. So we could break this up. We could write this as the square root of 500x cubed over 10x to the negative 1. I want to simplify this, so I'm going to have 500 over 10, which will just give me 50. And I have a 3 and a negative 1 as exponents, so that's going to give me x to the fourth. Right? If I move this up top, it becomes a plus 1. So I have radical 50x to the fourth, and radical 50, the square root, there is no square root of 50, so this is actually going to have to be simplified. I can't do anything else here. So I'm going to break it up into 2 radicals. I'm looking for my largest perfect square that goes into 50, which is 25 times 2 will give me 50. And x to the fourth is a perfect square. All my perfect squares I put to the left. Then I could simplify them, so this gives me 5x squared radical 2. 5x squared radical 2 would be my final answer for that one. And now we'll move on to addition and subtraction of radicals. So I turn the page here. Addition and subtraction of radicals. I wrote they must be like, right? For them to be like, kind of like terms, they have to have the same variables, right? And they have to be raised to the same exponents. Right? Same variables raised to the same powers, or exponents. Since we're talking about radicals, they have to have the same index, square roots or cube roots. And they have to have the same radicand. Right? They have to have the same radicands. Whatever's underneath the radical has to be the same. So for example, if I had 4x squared cube root of 5y plus 9x squared cube root of 5y, these would be considered like, right? This is my coefficient, 4, and this positive 9, and this is the like term, right? They're both x squared cube root of 5y. They have the same radicands, they have the same index, they have the same variables raised to the same powers. The coefficients can differ, and they do in this case. So it's saying, I don't know what this value is, but I have 4 of these, and here I have plus 9 of these, right? They're like. I have 4 of them over here, 9 of them over there. So if I combine them, I have 11 of these x squared cube root of 5y, right? 4 of these plus 9 of these is 11 of these. Let's do some more. What if I had, this one looks horrible. Oh, this is a good one. Let's see. 4x squared y cube root 2a plus 6x squared y cube root of 2a plus 5x square root of 2. So we're combining these three terms, and what we see is this term and this term are like terms, so I could add them. I have 4 of them here, 6 of them there, so I have 10 x squared y cube root of 2a plus this guy I can't combine with anything, so I bring him down, 5x rad 2. And that would be my final answer. Some more examples? All right, give me a second to write down some more examples. I have to watch this video. So in these examples, why don't we pause it? You guys try these and then come back and watch how I do it. So you should hit pause now because I'm going to run through these. 8 radical 5 plus 11 radical 5, they're like. So 8 plus 11 is 19 rad 5. Here I have 4 radical 13x minus 6 radical 13x. These are like terms or like radicals. So 4 minus 6 gives me a negative 2 radical 13x. And for this one, we have radical 20 plus 6 radical 5. Well, these are not like radicals, but radical 20 can be simplified, right? We could break this up as 4 times 5 is 20. Radical 4 is 2. 2 times rad 5 plus 6 times rad 5. Well, now these are like terms, so 2 plus 6 is 8 rad 5. We have one more example, big one on the next page. So you might want to pause it, write this one down, and attempt this problem. If you're going to attempt this problem, I would suggest that you do it in 1, 2, 3, 4 different radicals, and do each one and work it all the way down, and then see where it goes. So in this case, I have 3x squared, and I could break up this 54 as 9 times 6. 9 and 6. Y is not a perfect square, so it's going to stay over there. Minus 2x. I could break this one up. I'll give myself some room here. 24 is 4 times 6. X squared is a perfect square, and y is over there. $96 What is this going to be? Like, is it 16 and 6? I think it's 16 and 6. X to the fourth is a perfect square. Y is not. And then over here, I have my 4x squared. It's getting sloppy. 63 could be broken up as 9 times 7y. All right, let's see if I could clean this up at all. So I have 3x squared times 3 times 6y. So this is really 9x squared rad 6y. And then here I have a negative 2x times 2x, because the square root of 4x squared. So that gives me 4x squared rad 6y. This gives me the square root of 16x to the fourth is 4x squared rad 6y. So I have 4x squared rad 6y. And here I have 4x squared times 3 times 7y, which gives me 12x squared rad 7y. So it's really like 4 different problems all mashed up together. And now we have to combine like terms. Like term, like term, like term, not a like term. So I want to add these all up. 9 minus 4 is 5. 5 minus 4 is 1. So I'm just going to have 1x squared rad 6y plus 12x squared rad 7y. That's my final answer. So check your work and see how that works out for you. So the problems we worked on were mostly square root, but these same properties work with fifth root or cube root or anything. So if we look at these two examples, if you want to pause it, you could try them on your own. In these two examples, this says 6 fifth root of 3 plus 2 fifth root of 3, right? They're like terms. So 6 plus 2, this would be 8 fifth root of 3. This next example says the cube root of 24xy to the third minus y times the cube root of 81x. Well, right now these don't look like terms, but just like prior, we could probably break these up as perfect cubes. 8 times 3 is 24. X is not a perfect cube, but y cubed is. So this one's going to simplify. Cube root of 8 is 2. Y cube root of 3x. And on this side I'm going to break these cubes up. What's my largest cube that goes into 81? I think is 27 times 3. And x is not a perfect cube. So I'm going to have over here, the cube root of 27 is 3, so I have 3y cube root 3x. So now we have like terms, 2y, 3y, cube root of 3x. So 2 minus 3, negative 1. You don't have to write the 1, of course, so just write y cube root 3x. I think I'm going to stop there and start the next video on rationalizing denominators.